Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
So, Dr. Nahn, I'd like to start off by just getting some general background on things. For example, this is all about matter, and I'm not sure we understand fully what that is now that we have a selection of matter, dark matter and baryonic matter and so on. And so what is matter?
Okay, so I knew you were going to ask me this, so I looked it up, and the Oxford English Dictionary says matter is that which occupies space and possesses rest mass.
Okay, that doesn't
which
help
doesn't
me.
help at all, right? So what I think of as what is matter, I kind of think about, at one time I had young children, and they like to build with Legos, and they would build all sorts of creations out of these basic building blocks. And so they would take a couple Legos and stack them all up and make a beautiful house or a Star Wars character or something, right? And so matter is sort of nature's Legos, and what we're trying to find out is what the most fundamental Legos are, right? Pretty much our everyday world, people know, well, what are you made of? You're skin and bone. Well, what are skin and bone? Well, that's certain kind of molecules. Molecules are made up of different kinds of atoms, like mostly carbon, and water is H2O, that's 2 atoms of hydrogen and 1 atom of oxygen, right? So atoms then are made of protons and neutrons. That makes up the nucleus, and electrons, which circle around the nucleus in funny ways. And that the way they interact gives you all of chemistry, and chemistry gives you biology, and biology gives you us. But what we're trying to figure out, is there anything smaller than those protons and neutrons and electrons, the stuff that we think makes up everyday matter? And we've known, actually, for about 45 years that indeed there are smaller constituents of matter, and they are the subatomic particles. So in fact, the electron does not seem to have any smaller subcomponent, but the proton and the neutron, this is what we found out a while ago, 45 years ago, the proton and the neutron are made of things called quarks. So this is really what the goal of fundamental particle physics is after. It's what are the most fundamental building blocks of nature. And it turns out that there's a very easy, it sounds complicated, right? Fundamental particle physics sounds complicated, but it's actually very straightforward. There are essentially 12 things which make up matter. There are 6 things called quarks, and there are 6 things called leptons. The quarks are the up and down quark, the charm and strange quark, and the top and bottom quark. And it's 2 ups quarks and a down quark make a proton, 1 up quark and 2 down quarks make a neutron. That plus the electron gives you everyday matter, right? And the electron, its neutrino, and the 2 quarks make up what we call the first generation. Then there are 2 more generations, which are almost carbon copies of the first one, except they're a little bit heavier. And we don't really know why there are 2 more generations. We don't really need them to make up our everyday world. They seem to be there. We don't know why there's not yet another extra generation. So those are the kind of questions we're trying to answer. Is this all there is? Or could there be more? Now there's another piece of the puzzle that you have to understand, which is if you just have a bunch of stuff laying there and it doesn't interact, it's not very interesting. So how this matter interacts is another piece of what we study. And we talk about this in terms of forces, right? And people actually have heard about forces. There's electromagnetism, right? And that has a particular force carrier. So when we talk about electricity, really at the fundamental level, we're talking about some charged electron emitting a photon, which interacts with a proton over here. And that interaction makes the force. There are other forces that we know about, though. There's the strong force. So the strong force is what separates those quarks from the gluon, or sorry, excuse me, the strong force is what separates those quarks from the leptons. And it's what holds the proton together, holds the neutron together, and holds them tightly in the nucleus. And it has to be stronger than the electromagnetic force, because otherwise the protons would all fly apart. So that's why we call it strong. There's the weak force. So the weak force is the force that's responsible for certain radiative decays. And its force carriers are the W and Z. I should have said the force carrier for the strong force is the gluon, and then the force carriers for the weak force are the W boson and Z bosons. So there's this stuff, and there's those three forces that interact. There's actually a fourth force that everybody knows about. It's kind of funny, actually. It's gravity, of course, right? Everybody knows about gravity, but we don't talk about gravity so much in fundamental particle physics because it's not really part of the subatomic world. To feel gravity, you need something the size of a planet to pull on you to feel it, and even that's not that strong, right? We can, use magnets to levitate people, and we don't have magnets the size of planets, right? So gravity doesn't play a very big role, and we kind of ignore it for fundamental particle physics.
Okay, now if we get this matter, then your big finding this year, the Higgs-ish, is the Higgs-ish is then has to do with the mass. And so where does the mass come from in that case? And why is this an issue? Why don't these things just stick together the way they're supposed to?
Well, we have to be a little careful about what we talk about when we really mean mass. So there's sort of three effective definitions of mass. So sorry. Well, it all sort of makes sense, and it hangs together if you think about it for a while. But it takes a little bit, so we'll go slow.
Yes. Thank you.
So first of all, Newton came up with the idea of mass is the stuff which keeps you from slowing down quickly or keeps you from speeding up quickly. It's called inertial mass. Right? If you push on something with a certain force, it accelerates. But if it's really heavy, has lots of mass, it doesn't accelerate very much. If it's very light, it has very little mass and it accelerates a lot. So there's inertial mass, and that goes with this famous Newton's formula, F force equals mass times acceleration, which, well, if you've ever taken one of my classes in classical mechanics, you better have learned.
I learned this one.
That one people may be familiar with. The second form of mass, which Newton also figured out with a big hint from Kepler, is mass is sort of the source of the gravitational force. Right? Objects pull on each other with the gravitational force according to how big their mass is. And the fact that the gravitational mass is the same as the inertial mass it's what we call the equivalence principle. We call it a principle because we don't really know why that is, but it seems to be true. And if you think about it, that's what Galileo showed us when he took a big heavy thing and a light thing and he dropped them from the Tower of Pisa, and they fell at the same rate. That's because since the gravitational mass on this side equals the inertial mass on that side, the mass cancels out, and it doesn't matter. If it's heavy or light, it still falls at the same rate. So that's the second kind of mass. The third kind of mass,
drum roll,
yes, is the mass we're talking about. And this is the mass that our friend Albert Einstein gave us, right? This is the other physics formula that everybody probably knows, right? E equals mc squared. It says that a particle, or a hunk of matter, even when it's not moving, has a certain amount of energy called its rest mass. And this is the mass that we are dealing with in fundamental particle physics. Now, I have to be really careful about this now, and this is the thing that people don't really get right away. Quark 2 plus quark 3 gives you the mass of the proton. That's actually a very small component of the mass of the proton. So when we talk about this rest mass, we're really only talking about the mass of the quarks and the mass of the leptons and the mass of the force carriers. We're not talking about the mass of the proton or the neutron. So it's tricky because there's mass in the form of the interaction, and there's mass the rest mass when it's just sitting there. Okay, so the big problem, so we have this standard model of particle physics, and we've tested it so much over the last 40 years, and it always comes out with flying colors. It's actually a little bit depressing for an experimentalist.
That's right, you get tired of that.
You get tired of confirming the theory all the time. However, it has some problems. And one of the problems it has is that what it does is it predicts the probability for a certain event to happen. And if you allow these quarks and leptons and these force carriers to have mass, then at some extreme extrapolation of the theory, it predicts probabilities bigger than 1. Right? So the theory says either those things cannot have mass, or it doesn't make any sense at some extrapolation, right? So that's a problem for theories. They should make sense all the time, otherwise they're not a very sound theory. And this Higgs mechanism was invented precisely to fix this problem, to be able to have a self-consistent theory, but to allow those particles to have mass, because we know they do. We've measured it, right? So we know they must have mass somehow, and that's what this Higgs does. But it requires one new particle that we hadn't found. And maybe we still haven't found, but we can get to that a little bit later. And so you have to add a new particle, and then you say, well, the theory says there should be this particle there, and then you build experiments to go look for it. And this summer, we came up with evidence for a new particle that fits the description of a Higgs, right? But we haven't quite verified all of the details yet, right? It looks like it's in the right spot. It would make the theory happy, but we have to make sure that it has the right properties that a Higgs boson should have. In particular, it should be a spin 0 particle, and it should actually couple to mass.
Okay, and it has to be some size, in some size range?
Well, I wouldn't say a size, well, it has to,
you know what I mean?
It has to live in a certain range. Its mass itself has to be larger than what we searched so far, because we haven't seen it.
Right.
But it has to be smaller than a certain amount, otherwise the theory breaks down again.
Okay.
So it has to be within this range, and that's the great thing about the LHC, is we knew when we built this accelerator that we should be able to explore that whole range.
Right.
So we'd say, well, either we find this thing, or it's not there, and we have to, go back to theory and try to figure out some other explanation for this.
Or get a bigger collider.
Well, no, that's the point.
Oh, it
for
should
this
be able
particular
to do it.
one, we can see the whole range. We don't need a bigger collider at this point, which is very different than other theories. For instance, inventing more particles, they could always have too much mass, and we don't have enough energy to create those. But this Higgs one, either we find it, or we get to throw the theory away and try something new. That would be fun.
Okay, so then this makes matter possible. This is like a field to provide mass. Otherwise, it wouldn't be sticking together. Is that the idea? We wouldn't get it.
Say the mass of the electron is because of the way it couples with the Higgs.
Okay, and there are two things very quickly here. Then there are some particles evidently that don't have mass or have such minimal vanishing mass that it doesn't make sense. How did they escape from having mass? What happened to them?
Okay, so there's I think two particles you're alluding to. One are neutrinos, and for a long time we thought neutrinos had no mass because we couldn't measure it. But recently means in the last, say, 20 years, we have found that neutrinos do have mass. And we found this through a unique phenomenon in particle physics called neutrino mixing, where one kind of neutrino, say a muon neutrino, can turn into a tau kind of neutrino. And they can only do this if they have mass. So since we've seen them do this, we know that they must have some mass, even though we can't measure it.
Right. That's very interesting. I didn't realize it was because of that conversion.
Yeah, it's because of that's how we can know that they have mass. Now, the flag bearer for massless particles is the photon.
Yeah.
Now,
it's so special in so many ways.
Yes, which is the force carrier of electromagnetism. Yes, and it brings us the light from the sun, which is a very good thing for here on Earth. So the photon is it's a trick though, because in fact this Higgs mechanism, it was known that this Z boson and this W boson, they have large mass, but it was known that the photon didn't have mass. So the theory has to fit the experimental evidence, and the Higgs mechanism is specifically built to leave the photon massless. So it's part of the theory, and it's actually a very detailed part of the theory of exactly how this works, that preserves the masslessness of the photon while giving those other force carriers mass. So it's kind of like the fix is in for the photon.
Yes, exactly. I understand now. All is clear.
Is that okay? Wow, surprising.
Got through your
usually
course.
It takes a couple times.
Through this now. So you get this massive collider. Then, how does that work? How does it create these scatterings.
So accelerators are nothing new, and actually almost everybody up until 10 years ago had an accelerator in their living room. They didn't know it. It was part of their TV. A cathode ray tube is an accelerator that shoots electrons at phosphors and makes your TV light up, at least until the era of plasmas and such. However, those accelerators don't go to very high energy. We need an accelerator that goes to the very highest energy we can get, because you remember from Einstein's phase equation, E equals mc squared. We're looking for something with very large m, very big mass. You need very high energy. So when you have high energy particles, they also have lots of momentum. And you have to, in a circular accelerator, you have to bend them around. So something with very high momentum, it's hard to bend. So it helps you to have a very large tunnel so they don't have to bend so fast to go around in a circle. And that's why we have this 27-kilometer circumference Large Hadron Collider, which can accelerate particles eventually up to the highest energy, which is 14 tera-electron volts.
And so now it's not generating that speed right now, but
at the moment that energy, it started at 7, and then it moved up till 8 tera-electron volts. And then we're going to have a little shutdown for about 20 months at the end of this year, actually sort of next January, I guess, or February, where we actually install some more instrumentation so that we can make that step up to 14 TeV confidently.
And then look out, right? All the lights will go out.
Well, who knows? If there's a new particle that we can't quite reach at 8 TeV,
yes, right.
As soon as we get to 13 or 14, we may suddenly say, hey, we got something new again, and everybody gets excited.
Well, since you're on that, then could this go on like exponentially? That you could just
there's
build
only
larger and larger and larger
You're sort of fixed by the radius of your tunnel, how big your tunnel is, because if you try to put too much energy, it won't make the curve anymore. And the strength at which you can make the curve. And that is related to the magnetic fields. So actually, the magnets in the LHC are run at 1.9 degrees Kelvin. That's 1.9 degrees above absolute zero. And they are 8 Tesla, which is very, very strong. And they are actually, part of the limitation of to what energy we can go to.
Right. Is there any way that you could make a linear kind of collider?
Absolutely.
Is there any advantage to one or the other?
Yes, there is. So with a circular collider, you get the advantage of recycling, right? You get several passes where they can collide at particular points where you put detectors to do the measurements of the physics. For a linear collider, you only get one pass. On the other hand, in the case of linear, you don't lose so much energy when you're accelerating. So it sounds funny to lose energy while you're accelerating, but there's some maximum amount you can push. And in a circular accelerator, that maximum is less. You can't push so hard, or you just lose all the energy from what's known as radiation. Bremsstrahlung is a German word. But basically, as the particle goes in a turn, it actually shoots off a bunch of energy in the form of radiation.
So it doesn't.
If you go straight, you don't shoot off that energy. You don't lose it.
Right.
So
you don't.
There are advantages and disadvantages, and there is a proposal actually to build the next collider, which would be a linear collider, with something like legs that are 30 kilometers long in one direction and 30 kilometers long in another direction. So we'll see if that can be built. It's a kind of a hefty price tag at the moment.
Yeah, I'm sure it is. And speaking of that, the attempt to build one of these things and sort of own it in the United States and Texas years ago and so on, and Congress voted it down, and ultimately after they got it started, got started building and stuff. Do you expect that you're going to have huge international projects around this sort of thing by necessity in the future?
Yes, I think that's clear, right? And CERN is a great example of that. So at CERN, there are 20 member states. And in fact, if one of them, if their politics dictates that they can't participate and they're going to pull out, then it's disappointing, of course, but it's not a catastrophe. And in fact, this happened. Austria threatened to pull out a few years ago, and everybody was like, oh, don't go. And they turned out they didn't go. But it's not going to end the project at CERN. Right. And there's also, the US, for instance, has observer status, and we also contribute a lot in terms of resources and financially to CERN, especially the experiments themselves.
Right, but it makes it all more doable,
But it makes it more doable, and it makes it a bit more robust.
Yes. I see that. Yeah.
So because it's very hard to find, the long-term commitment. You need, 20, 30 years to build one of these things that really pushes the frontier. The Hubble Space Telescope is another great example.
Yes.
A long-term project that you need to be able to support that whole time. And so that's a little bit hard to come by.
Right.
When people think of this as a luxury.
Exactly.
I don't think it's a luxury.
It isn't
I think
a
you
luxury
absolutely
anymore.
need to do this
right.
kind of,
and we'll definitely come back to this. That's a very important point. But I got off a little bit there. I meant to ask you about doing the data now. So it's CERN. Okay, so you bang these things together.
Oh yeah, so you bang those things together.
Show us
and then
these
you have to
pictures.
measure them. So what we have is essentially a what you can think of it as a 100 megapixel camera, right? That is 20 meters long and 15 meters tall, and it has a bunch of different filters on it. So those are actually the subdetectors, are the different filters that measure different aspects of the event, and it clicks at 40 megahertz, or once every 25 nanoseconds. So that is a huge amount of data to be moving that fast, right? And so then we have to make up a whole series of high-speed electronics to be able to, from that original data sample of 40 million events a second, we throw out we keep one out of, say, 10,000 that contains the most interesting physics to us, right? And that has to be all done in the matter of microseconds. Then you go to the next level, and then you have milliseconds to look at the remaining interesting stuff in more detail and find out what is really the most interesting events. And from there, you can actually write that to a disk, because that's what disk speeds allow these days. So that's the whole online process. And along with this goes a lot of monitoring and power supplies and temperature monitoring and control and humidity control and safety systems. And the enterprise is enormous.
Exactly.
So,
exactly. But there's a lot of that sifting that's instantaneous.
Yeah, there's a
I don't
lot
think we
of
knew
that sifting.
With the data. And then what happens to this?
Then you have disks, and you store petabytes and petabytes of data on disk at various places around the globe, actually not just at CERN, but at Fermilab in Illinois, for instance, as well. And then the person who wants to do an analysis decides, what is the signature of the physics I'm looking for? Right. If I'm looking for Higgs, maybe I'm looking for its particular decay to two things called Z bosons, which then decay to electrons and muons. So I write some software that sifts through the data and looks for these particular kinds of events. And I take that piece of software, maybe that takes, depending on if you're bootstrapping off somebody else's code or if you're writing it from scratch, it can take weeks to months. You test it all out, and then you submit it to what's known as the grid, right? Which is essentially a mechanism for telling your job, your program, I want to look for this kind of data. You tell me where it's stored. You go off, ship the program to that location, run it on that data, and just return to me the results. So I may sit at my computer at MIT, and I may submit my job, and the job goes off to Taiwan, or it goes off to Italy, or it goes off to Germany, and it runs on the data sample is actually resident there, or it goes to Fermilab maybe, and then my results come back to me. So there's this whole network of computing, distributed computing, that we've built at to handle the analysis that has to be done at the LHC. And running over all the data, depending on how clever you are with your cuts and identifying things, can also take, it can be a few days to 2 weeks. It also depends on how many slots, how many computers you get running at the same time on the data, that sort of thing.
I see. And then if it's something like the Higgs, where you need to verify, and it seems as though, well, you've got these parameters here to there or something like that, then how long does it take to
Well, that takes a long time, too. I mean, first of all, I should say that there is no single one person in my experiment who is doing the Higgs, right? We have many, many people who are all, we have redundancy in terms of analyses, we have people cross-checking other people. So, there's probably 400 people all trying to measure the same things, maybe in different channels, that sort of thing.
Right.
So, and then our scrutiny process, we actually have to get it through our collaboration first before we let any results go public. And that is where you face your peers who are also your biggest critics.
Yes.
Right? So there is an enormous amount of cross-checking and making sure that it's consistent in this channel and this channel, and these people see the same thing, and you even down to counting, did you remember the exact same number of events, and are they the exact same events as this other team who is working on the same thing? And that process can also take maybe a month or so, maybe longer. It depends on if it's a high priority analysis, a result we want to get out right away, or if it's something that is not so, say, controversial or won't make headlines in the New York Times, that sort of thing.
Exactly, exactly. Some subtle things, right? But so on the public side, the non-specialist side, we can be pretty sure when they say something is the Higgs-ish that in fact it is the Higgs-ish.
Yes.
Okay.
Yes. I mean, and that that's why some people will say, well, they're hiding their results. We're not really hiding our results. We're just making sure that we trust our results before we spread them out among the public.
Right.
And in this case, we have sort of the gold standard from 2 different experiments that say what we found a new particle, something that we didn't know was there before. Right. Whether it's the Higgs or not, well, we sort of have to look at it and make sure it has all the properties that a Higgs boson should have. So that's why it's Higgs-ish.
Yes.
It's certainly consistent, but we have to check. And so right now we're in the process of checking whether this new thing has all the properties we would expect from a Higgs boson before we can give it that name without the ish.
Right. Now, you've talked about this army of highly specialized people, and I'm wondering, as an experimentalist, what does that bode for future training of say, particle physicists who want to work in this kind of a field? I mean, what does that mean? If you have specialized kinds of training, what goes on now? What can people expect?
Well, I think that it's certainly hard in terms of, certainly there are fewer and fewer of these types of experiments. And that's partly because they require so much resource and so much time that, it takes a while to even get the technology base in one place to actually build something like this, right? And so what that means is that if you want to be a particle physicist these days, CERN is sort of the only game in town. And there are people who are doing other things. You can use you can use natural accelerators that would be, cosmic processes, and you can look for particles coming in the form of cosmic rays and try to do discoveries there. That's particle astrophysics. And there are trade-offs. The accelerator never breaks down when it's nature. It's always there. On the other hand, the rate is much, much lower. And it's not as easy to tell how the initial state, we would say, was prepared, because you don't really know where these things came from. You're just looking for them. So some people turn in that direction. But I think, it's getting more difficult to do these kind of experiments. I think, so the accelerators are working well. I always say this about the LHC. The accelerator is working very well. It's delivered plenty of data for us. We're very happy with it. The detector is also working surprisingly well. To my mind, I would have thought we'd have a few more bumps in the road than we have with the detector, but we haven't.
Something so complicated.
The tricky part is getting all the people going in the same direction. I mean, some of my colleagues have said, we are a collaboration of 2,000 or 3,000 people. There's no CEO. There's no boss, right? So these people are always trying to work together, and there is some sort of organization, but no one has necessarily command of everybody else or has the ability to fire anybody. So the fact that we get anything done at all is somehow a miraculous
exactly, which is something to look at. I mean, maybe you shouldn't spread the word that there's nobody
we do all have one goal. I mean, we're all interested in the physics in the end. And when people get competitive about whose result is actually going to be the one, then you sit back and you say, well, it's really about the physics, because that's what we want to learn.
We rise
It doesn't
above
really
it.
matter who actually produced it, because, I mean, in these situations, many different people could produce the same result.
But one of the things I wanted to find out was that when you were preparing, when you were working on your doctorate, you were involved with people who were right in the middle of everything. Is that, for your students now, is that still a possibility?
It is a possibility. And I would say that, it's not that the LHC suddenly we changed how things worked. This has been going on for a while in particle physics. The collaboration I worked on, 20 years ago had maybe a few hundred people. The collaboration I worked on 10 years ago had maybe closer to 1,000, and now we're up to 2,500, 3,000 or something like that. So it's been kind of an evolution in this direction. And that's just because as you get the higher energy, the things get more complicated, you get fewer of them, and people sort of congregate together, both to pool the resources and because there are fewer places to do things.
Yeah.
So, you know, and it is possible. I mean, we send our students over to the lab, and they work there for a few years. But it's getting harder. It's getting harder to do that. Geneva's not a cheap place to go to, actually.
It's true.
So
Right.
It's getting more difficult, and we worry also about students getting the full experience. Building these detectors only happens once every 2 decades, 3 decades. So how do you train your students? And in fact, the American Physical Society's Department of Particles and Fields has brought this up and has a special program to try to give students opportunities to learn the hardware side of the techniques we use, not just the software side.
Exactly, you can't just sit back and think
well,
it out.
yeah, and you don't want to give the student the detector while it's taking data and say, yeah, play with it. You can't have them do that, right? So,
be a thought. That would be a thought. Okay, then I want to ask also about the future, just in general. You've already mentioned these things are supersized kinds of machines. They're very expensive and so on. What is the future for what they will be looking for what this, I'm assuming we're going to stay with this machine, and what can be looking for,
so,
and I wanted to touch on supersymmetry when we get in here too.
Yeah, so the danger here is that, so we say, oh, we found something, and everybody said, good, you're done. No, we're not done.
Right,
in fact, we want to study it. We want to make sure it has all the properties and everything we expect, because it could be that this is the first of a few things that we find.
Yes.
And then it's not the Higgs-ish boson anymore, it's something more. So that's goal number one, is study this as much as possible. And in fact, this year's data taking plan was built precisely for that, to try to get as much data as we could before we go through the shutdown to really nail it down.
Right.
So the second thing is, it's not the end of the story. So even if you have a Higgs boson, it actually still causes problems with theories that start exploding, predicting probabilities greater than 100%. And there are ways to fix this, many different ways that involve more new particles. One of the most popular ones is what you mentioned, called supersymmetry, or people call it SUSY for short. And the problem with the Higgs is, if I can describe this using a kind of a ludicrous analogy, right, is that you have contributions to its mass. Its mass we measure now. We know it has this finite value. You have these enormous contributions on one side driving it positive. You have some enormous contributions to its mass driving it negative. And these just magically cancel out. It's like throwing 3,000 elephants on one side of the seesaw and 9,452 rhinos on the other side of the seesaw, and it just perfectly balances. Seems a little unnatural to us. Unless there's a mechanism underneath that causes, that, you know, basically forces this cancellation. And supersymmetry was invented, at least the way I learned it, to actually solve this particular problem. For every particle, you invent a supersymmetric partner to a particle, which gives you an equal and opposite contribution. So all those positive contributions get an equal and opposite, so get a negative contribution of equal strength, and the negative ones get a positive one of equal strength. And so it's sort of built in. The cancellation is, the fix is in. It's built in.
But it is a fix.
Right. Supersymmetry also has some other very attractive properties. We haven't talked about it, but there's this idea of dark matter.
Yes,
what is dark matter?
The next question.
So dark matter, we don't really know what it is. We know it interacts gravitationally because of the way that the stars and galaxies are moving. They're moving too fast way out there for there not to be some more mass. But we can't see it. It doesn't interact with light, so we call it dark. It's dark and it's matter because it interacts gravitationally. Maybe one of the slew of supersymmetric particles have enough mass that they could be candidates for the particulate form of dark matter, right? So, and in fact, there's a nice little confluence of theories where, at the scale that you can measure with the LHC, if there is a supersymmetric particle, it could solve this dark matter problem. It's in the realm of possibility. It's in the right ballpark on all sides. And the other thing is sort of an esoteric thing that theorists and physicists, I should say, like, which is we know that at some high energy, actually, the electromagnetic force and the weak force get unified into sort of one theory that when you go to low energy, sort of splits into two, right? we would like to actually even be able to take the strong force and unify it with those. And it looks like we can do it, but not quite. They just miss unless you add supersymmetry. And then they coalesce at some very high energy scale. So this is sort of a, I mean, this is a reductionist, physicist. We like to be reductionists.
Right,
We'd like to think of there as
right.
one theory, which then if you take it to one extreme becomes maybe three.
Right.
So supersymmetry also has that added feature to it that people like.
And that can be, the LHC can be the source that will help you get to the bottom of that.
Now, the difference between the Higgs and supersymmetry is the Higgs has to lie within a certain range of masses. Otherwise, well, below, we've looked, we don't see it there.
Right.
Above, the theory doesn't make any sense.
Right,
There's no reason to have a Higgs. The LHC covers that whole range.
Right, okay.
Supersymmetry, below, we've looked, we don't see it, but there's no upper bound. So it could always be that, well, the LHC just doesn't have enough energy to produce supersymmetric particles.
Right.
If that's the case, then we need a higher energy machine. And that is what people will be excited about when we go through the shutdown and come back at a higher energy.
Right. And on this, then, we're higher energy machines and so on, and looking into the future and winding down here, then we are trying in this organization to garner support from the public for projects in science, or for science in general, that because science is very much in the center of modern life. And if we're going to figure things out, we're going to figure them out pretty much through science. Well, these kinds of projects take many years. They take, as you've pointed out, vast numbers of people and very large resources, and they need to be international now. So do you foresee that, like, the support, the international support, for the political support, wherever it is, that will help finance these kinds of things?
Yeah, I mean, I think it's a tricky issue, and it's hard because people do see these sometimes as luxuries. On the other hand, I go and I play soccer with my team in Arlington, and they all ask me about what's going on with the Higgs boson. So it's clear that people are very interested in this, and people have to, people are interested in finding out new things about the world. Whether that translates into the politics of funding science for science sake is less clear to me, right? And people ask, well, what does a place like CERN bring you? And so I have some answers. One is innovation, right? People say it costs a lot of money actually to run these things, and that's true, but it is spread out over decades and decades, and it does
produces stuff,
other stuff. So the canonical example of this is the fact that in order to get scientists to communicate with scientists, there was a guy named Tim Berners-Lee.
Yes.
And he coined the terms World Wide Web.
That's right.
Uniform Research Locator, whatever URL stands for. HTML.
Yes.
Right. The reason you know about those things, the reason those came into existence, was because of science for science sake.
Exactly. Yes.
Right. So if you say CERN is expensive, I will ask you, what do you think the internet is worth?
Exactly.
And because that's one of the payoffs.
Exactly.
There are other examples. There's a lot of examples. There's proton therapy centers, which are good for treating cancer because they deposit the energy in a localized place around the tumor and not in a bunch of other healthy tissue near the tumor. Right. These things are being built by lots of hospitals. Who knows how to move protons around, steer them around, make magnets that you can use to do these things. That would come out of actually the research that is for CERN.
Right.
So there's innovation.
Right.
There's also expertise. Right.
Yes.
I have friends who don't stay in particle physics, but they go off and they run the isotope production plant in Mass General Hospital, so that people can undergo, diagnostic radioactive therapy treatment and diagnosis. Right. Because they know how to run accelerators and know how to produce isotopes. I have friends who look for oil with neutrons. I have friends who go off to Wall Street and apply some of these
Don't
algorithms.
talk about that, right?
Oh, sorry. Yeah. Well, I have to mention them. Hopefully they're listening. I have a friend who works on luggage scanners. Right. That's a lot like a particle physics experiment. You take a quick picture. You look to see if there are any illicit items in the luggage, and you want the best resolution. You want to make the decision very fast. Right. It's very relevant. So there's all sorts of expertise that's generated from
all
this.
these things spill out of
Yeah.
it, but it's also the future, and it is true that if we're going to go into space, that we're going to need telescopes, we're going to need all of these kinds of things, and to get down, drive down, and to find out what reality is, then this is the way that it's going to do it. We don't have options like there's not some tiny thing we can use here.
Yeah, yeah. There's no direct killer app for the Higgs boson,
Right.
right? There was no direct killer app for the electron either 100
Yes,
years
this
ago
is true.
when J.J. Thomson discovered the electron.
Yeah.
And now look at how many things we can do because we can move the
Absolutely.
electron around.
Exactly.
So what the payoff will be 50, 100 years from now, you really don't know. No one would have predicted 50 or 100 years ago what we have today, I would guess.
It's amazing.
So,
it's really amazing. It's true, just 50 years ago, but think even 100 years ago, the difference is just staggering of what we know today, and we in the public hope we can catch up with, with the information. Dr. Nahn, thank you very much for giving us this wonderful information. I'll turn it over, let you all ask a few questions until they throw us out. Thank you very much.
thank you.
If there is a fundamental difference there between the field and the particle, should I then also assume that there's a fundamental?
I think the answer is yes to all your questions. It's germane.
Okay.
There is a Higgs field and a Higgs particle. So the Higgs boson is the excitation of the Higgs field. It's the Higgs field that permeates everything, but the boson is actually sort of if you think of like a surface of water, right? That's the field. A wave is an excitation on the surface of the water, right? So that is sort of in sort of the simplest picture I can conceive of, an analogy to what the Higgs boson is versus the Higgs field. But yeah, I mean, these things are built on quantum field theory, so the theories of actual fields interacting. Just like in electromagnetism, there was a field, an electric field and a magnetic field. But the way we envision sort of the Higgs as an excitation of the field is the same way we think of the photon as representing the electric and magnetic fields as well.
Okay, so the problem here, how could the Higgs particle be massive without the property of massiveness?
Yeah, no, this is tricky. It's because the Higgs can interact with itself. And this is different than electromagnetism.
Yeah.
You think of a photon as not charged, right? So it doesn't interact with itself. It interacts with charged particles like protons and electrons. The Higgs itself is, to some extent, charged. So it interacts with itself, and it gives itself mass as well. So there is no chicken and egg as long as you can have this self-interaction. Maybe a little technical. Sorry.
That's right. But it does derive, the Higgs boson does have a property that we call mass.
Yes.
And you're saying it derives that property from itself.
Essentially, yes.
Wow.
Wow.
It-
Is there a Higgs field in this room?
yes.
If I had a Higgs meter, 100 years from now, I could detect it?
Yes.
Does it have a gradient?
Ooh, good question. Does it change in space and as you move from here to there? Well, that I don't know. I have to think. What my equations tell me about it. I don't know that anybody's thought to ask the question of does the field have a gradient. I would guess it does. But it's supposed to pervade all space and time. If it has a gradient, it's kind of hard to talk about gradients the way you talk about like a gradient in a temperature field with the Higgs. This is quantum field theory, so not sure that it makes sense on that scale, right?
I'm asking you.
I know. Well, I'm thinking for you right now. So, I mean, I think you can say yes. It definitely, if I'm picturing the quantum field theory language of how they actually encapsulate the Higgs in quantum field theory, and there is a gradient involved there. Yes. Whether you could actually measure such a gradient, I think not.
But if I could measure a Higgs field with my Higgs photometer 100 years from now, doesn't that imply a gradient if I'm able to measure it? If it were totally uniform forever, like the ether.
Yeah, why would it be
Higgs field
there?
the same as the ether.
Yeah. Why would it be there? I think you can measure the Higgs field, but you wouldn't see it that way. What you would do is you would probably be able to, the fact that things have mass would tell you that there's a Higgs field. right?
You mean you could infer it?
I think you'd have to infer it, but it's not clear to me that unless you had, I don't think you would have the ability to actually see a Higgs boson. I don't know. This is quite speculative,
So maybe
I would
my
say.
meter will never exist. I don't
Yeah.
So then the rather expensive experiments, quite apart from LHC, that are proposed or underway to detect the projected existence of gravity waves, would that affect your understanding of the Higgs boson?
No.
Waves are detected?
I think not. I mean, gravity waves, I think I said this before, gravity we don't really talk about in so much in quantum field theory. I mean, there are ideas about a graviton, but that is very different than gravitational waves. Gravitational waves are caused by really huge, massive objects like black holes colliding and sending out these waves, and you need something that big to make a gravitational wave because gravity is so weak. So Higgs mass is really about the rest mass of particles, where gravitational waves has more to do with gravitational mass and how gravity interacts and actually changes. Well, this is, I don't want to go there because this is not a talk about gravity, and I'm not an expert on gravity, but gravity mass itself, gravitational mass, changes the shape of space-time, and that's what these waves are. So they're really quite disjoint, I would say. There's no way you can start with Higgs and you get to gravitational waves.
Einstein made a significant contribution, infinitely small but infinitely large.
A need? I don't know, we might be branching into metaphysics here, actually, right? I'm an experimentalist, so I make observations and see what is there, as opposed to saying we absolutely need to have a unified theory. We'd like it, and we see examples of this already. I mentioned one before where electromagnetism unifies with the weak force, essentially, where we can see them as both coming from a single source. So if you could do that with then the strong force as well, and then you could do that with gravity, even though we don't have a quantum field theory of gravity even that we understand, then you would have one. But I don't think you absolutely need it, right? It's sort of a different philosophy, if you like. Some people could say, well, yeah, there must be something that underlies everything that you can take and just go this way. And in fact, these theories have a lot of the same mathematical concepts over and over again, so they are very similar. But they each have their own foibles, and it's not clear to me that there has to be a unified theory.
But perhaps it's desirable. You'd like to see it happen.
I think certain people would like to see it happen. I think other people probably don't care. So, you know.
But I wonder if Einstein cared. I mean,
He cared, I think, yes.
Yeah, he certainly would care. I don't know whether he had a preference, or whether he would have thought, you know, it doesn't have to be this way. But he would have certainly been interested in the question, for sure.
If I understood you correctly, you were talking about taking the data. I'm wondering if you're only finding the things that you're looking for, if the parameters...
That is a very tricky question, yes.
And so my basic question is there enough computing power available to you to process absolutely all of the data from at least one...
But there's a slight distinction with your interpretation, which is we look at the entire event. We just don't look at every single event that happens, right? Okay. So the filtering doesn't happen. I mean, as much information as we can get, and even the fact that we use things like energy balance to infer that there are particles that we couldn't see going that way because otherwise the energy would imbalance. So we look at every aspect of the event that we have a detector built to see.
And by event, that is a collision.
A collision. But the problem is we cannot deal with the slew of collisions that are coming at us. So what we have to do is build up something that says, okay, in this event, there's a bunch of energy there and what looks to be like a muon over there. So let's keep it and look at it some more. And then at the next level, we say, okay, that energy, we get a better resolution on it, plus we see some more things here that we have time to reconstruct, and that muon looks like a really good muon, and it has a sister muon over here. Let's really keep this, and then it goes to tape. Not only that, so that's called a trigger system. And you're right, you build it so that you select what you think is the most interesting physics. So you could be blind to something that you are totally not expected to see. On the other hand, we're not that dumb. We also, every once in a while, take an event no matter what. We just say, take this event, right? So if there is prevalent new physics out there that doesn't satisfy our filters, it should end up in that sample because we don't even use our biases in those. So we try to keep an eye out for that, right? But the fact is, these events happen once every 10 billion. A Higgs event is once every 10 billion events, right? So you really have to do the filtering. You cannot take 10 billion and all at once and then keep looking. See? So, sure.
We're going to have to
Last question. Has there ever been a proven occurrence of proton decay?
No, and we're looking.
And they're still looking, yes.
Absolutely.
And does negative mean something?
Does
the fact that they haven't seen it yet?
Yes, you can rule out certain theories that would predict that protons decay. Suppose that, like quarks and leptons actually come from something even smaller that we can't see, right? Then you could have a proton made of quarks, but those quarks could decay to this smaller thing, and that might disappear. So those kind of theories actually are ruled out by the fact that we don't see proton decay. And the limit on proton decay is the lifetime is something like 10 to the 33 years, which is well beyond the lifetime of our universe.
Which is why you need a big vat of water.
Exactly. And they have enormous vats of water where they look for proton decay, because you just need a lot of stuff. Yes?
Thank you so much. I've got to let this
Sure.
go.
I can go out and I'm happy to talk in the hallway if people have more questions.
And you had an interesting family. It's unusual, I believe.
Well, okay, so I originally, well, actually I was born in Germany, but we moved away from there after I was 3 months old and settled in the Midwest in Madison, Wisconsin. And my family, I think that's actually part of the reason why I'm in physics. I am the 7th of 8 kids.
Isn't that something?
Which
Wow.
is, yes, quite a household to grow up in, a little different than most other people.
Yeah.
And so part of the reason I think I chose to go into physics, well, first of all, it interests me, and certainly I had a certain talent for it. So it was always interesting to explore how the world works in the most fundamental way. Probably every scientist you have says that their scientist is the most fundamental, but physicists really believe that we're the most fundamental science and everything derives from us. And then the mathematicians come in and start talking about them. But okay, fine. Anyway, part of me thinks that, a lot of what I did when I was growing up and making decisions was just to do something different than the rest of my siblings. There was already a doctor and an engineer and a lawyer and an advertising guy.
Amazing
and,
family.
So, but none of them had done academia, and certainly none of them had done physics. And most of them get scared when I start talking about it now.
Yes.
But so I grew up in this big family in Madison, and I got my undergraduate degree there in physics, working actually in a space physics project to study the soft X-ray background with a sounding rocket. That was very fun, and I learned a lot of great engineering and apparatus skills, how to actually put together a detector there. And then I came actually out to Boston, and I did my graduate work at MIT. That's where I really started in particle physics. So I took classes at MIT, and eventually moved over to CERN, even as a graduate student, and lived there for 3 years with my wife, working on, it's actually the predecessor to the Large Hadron Collider, called the Large Electron Positron Collider. The same tunnel, just colliding electrons and positrons rather than protons and protons. And that's where I did my PhD, where we studied, we went up to the highest energy possible, and we studied production of pairs of Ws. First time you could produce pairs of Ws. That was my thesis topic, as well as a lot of other things. We also searched for supersymmetry, and we searched for the Higgs. We didn't find it because we didn't have enough energy. So after that, I decided, that detector I kind of inherited. I didn't actually build it. I didn't have a role in building it. It was built and running when I got there. So I decided I wanted to play a role in actually putting something together again, and I went to the Tevatron, which was just in the middle of a fairly long shutdown, to upgrade its interaction rate and upgrade the detectors called Tevatron Run 2. And there I really got involved in building a detector again, and eventually ran that detector and studied the physics of the B quark there. And then I decided to come back to MIT.
Yeah.
So they offered me a position, and I came back to MIT, and that's when I got involved in the compact muon solenoid, which is the current detector, one of the two big detectors at the LHC that's responsible for this, beautiful new measurement of the Higgs-ish boson.
Right.
We hope by the end of the year we can take the ish off of that.
Yes, right. But were you involved in the actual building of the design of the CMS2?
Not so much, because I got there, again, a little late, so the design was already in place. But we were really in the throes of putting the detector together. So you assemble it in pieces,
and
actually.
Drop it in the ground.
Yeah, drop it in the ground. Well, drop it is, maybe not drop, that's probably not the right verb to use. Lower it gently down to the ground.
It descended.
But yeah, so I was involved a lot in the integration of the detector and in establishing the first operations. And as I described to you before, this is like a 100 megapixel camera that's taking pictures once every 25 nanoseconds, so at 40 megahertz.
Yeah.
So getting all of those things firing all at the same time, making sure every piece of your detector is looking at the same event at the same time, the synchronization, the calibration, it's a huge effort. And it wasn't just me, right? It was me and a bunch of other people. But
to work on.
Yeah. So it was really, really fun. I was over there for 15 months in 2006, 2007, and since then, actually, most of my group is there keeping the detector running and analyzing the data, and I hop back and forth between teaching at MIT and going there.
And what's your main focus these days? You did all this work on the W before, and do you just progress right along? What do you do?
So my main focus has been on this Higgs boson. Partly, the LHC, the great thing about it is you're taking such a big step up in energy that there's a huge amount of different things, a plethora of things you could actually explore, right? You can go look for brand new particles that aren't predicted. You can try to solve this Higgs problem, which is sort of the last, corner piece of the standard model that we haven't really solidified yet. You can study heavy flavor physics, the physics of the B quark, for instance. You can look, it's a top factory, so it cranks out top quarks like crazy. And there are good reasons to look at them because they're so heavy compared to the other ones that maybe new physics will show up there first. There's just a whole slew of things you can do. It's like a kid in a candy store.
Yeah.
I picked Higgs probably because of my upbringing in, sort of at the Large Electron Positron Collider as a graduate student and at the Tevatron. Those were sort of the seminal measurements that really solidified our understanding of this standard model. So sort of, to me, the most satisfying thing to do would say, is this, model of weak interactions, electromagnetic interactions, strong interactions, it needs something like this Higgs. Is that the answer? And that's why I'm studying the Higgs.
Yes. And the future?
So the future is an interesting question, right? The future right now depends a bit upon what we find at the LHC. And this Higgs is a great start, because it in fact gives us, if everything which has mass couples to the Higgs, then suppose that you make something which produces lots and lots of Higgses and you watch them decay, maybe you see something it decays to new you didn't see before. So that's one example of what people are thinking about these days. Maybe we can build an accelerator that is a Higgs factory. And you'll find lots of talks on, well, I don't know, other people go to these talks, but I see lots of talks on, future accelerators to exploit that. The other question is, the Higgs is not the only thing we might find at the LHC. We're just sort of the tip of the iceberg, right? So again, if we find some more, if we find a new scale where particle physics, new particles sort of emerge at a new scale, then we would target an accelerator to produce exactly that scale so that we can tune it and we can really study the production of these new particles, right? Right now, it's sort of it's what we call a broadband machine. When you collide protons on protons, you're colliding a bag of stuff on a bag of stuff, and you can end up with a whole spectrum of different energies of actual collision, because you don't know what actually hit what quite precisely. If you do the same thing with electrons and positrons, now it's not a bag of quarks and a bag of quarks, it's a single point particle and a single point particle, and you know exactly the energy of it. And so you can study things much better. You don't get as good a search out of it because you have to move the energy yourself. The protons, when they're colliding, they give you naturally a whole spectrum of energies. So if something is sitting up here, that's within your spectrum. When you collide electrons and positrons, if something is sitting up here and you're sitting at this energy, you won't see this, right? So it's only after you found something that you want a machine like that to really study the physics. And that's what the particle physics community is talking about, is where can we build a new machine which gives us more access to this higher energy regime. But you want to know where that regime exactly is before you set down in stone what you're going to build.
Yes. So you anticipate more colliders, or another what generation of colliders?
That would be the next step, another generation of colliders.
A whole lot more of particle physics. It's not time to announce that's all been solved.
No, not at all, not at all. And I think there's many times when we said, okay, we got it all figured out, and then boom, quantum mechanics or relativity hit, and everybody said, no, we have nothing figured out.
Now people don't do that anymore, right? I suppose.
So I think there's quite a bit of particle physics in the future.
Yeah.
Now these are long-term projects.